So I want to stress some of the point that I made with some data, and this is, for example, an example of the constant voltage scaling and on the constant field scaling. Because in all those years from the 80s up until the beginning of the 2000s, the geometry of the transistors did not change that much except for the scaling. We observed a reduction in size and the reduction of the supply voltage, but of course the main geometry remained more or less the same, and also the materials remained the same. So this is source, drain and gate, and of course this is source, drain and gate. The oxide dielectric was silicon oxide. This the gate was in polysilicon, and I mean, there is not a big change. The operating voltage scaled less than the length, because in the initial years the operating voltage did not scale that much. This is 4 volts. We typically were used at 5 in order to maintain back compatibility with TTL logic. Now, many things have to change from 2005 in order to treat the problem of the leakage power. This is considering a typical microprocessor from Intel, the evolution in time of the active power and of the static power. So the active power is the dynamic power consumption. The leakage is the static power consumption. Okay, so at some point up to the 90s we do not see any variation, also because the threshold voltage was high, did not change, and therefore the off current was practically negligible. Then after 92 we start to decrease the supply voltage and also the threshold voltage, and of course we start to observe a very fast increase of the static power consumption. Okay, and the static power consumption goes faster than the active power consumption because it is exponentially dependent on the threshold voltage. So you start to see something very critical, because you see that at this point it is clear that the leakage power can become predominant and then increase even faster than before. Okay, so this was really a critical issue, and I already have shown this figure to you. This thing that happened in 2001, and actually was triggered by this observation of the leakage power. Basically, the power consumption of a microprocessor from Intel was more or less constant until 92, in this below 10 watt range. Then it starts to increase, and the prediction is that once the leakage power takes over, the increase is going to be even faster and completely out of control. So something had to be made. Okay, this was the problem that the semiconductor industry faced in 2001. You need to know that since the 90s, no, since the 80s actually, the Association of all Semiconductors Company prepared every year a document in which it foreseed, it wrote let's say forecast of the evolution of CMOS technology for the next 15 years. So in 2000 the report went from 2000 up to 2015 and so on. Every year is upgraded, and it's an interesting report because it says clearly what are the main challenges, the main problems, what is the possible evolution, and it is something it's something that actually tries to predict and to sustain the evolution of Moore's law. And also it is something that is important to, let's say, to satisfy for all the large semiconductor companies, because if you cannot sustain the forecast of the industry for the next 15 years, probably at the end of the 15 years you are completely out of the market. Okay. Now in 2001 the problems were pretty clear. I don't know if you can read the table in the back. I will give you, of course, the table, but this line is important. Is the physical gate length of high performance MOSFETs. In 2001 was 65 nanometers. The prediction down to 2007 was to go from 65 down to 25 nanometers. Okay, and the equivalent physical oxide thickness of the gate dielectric was at that time something close to 1.5 nanometers and had to go down to less than 1 nanometer. Okay, these colors are important because red means we do not know how to do it. Okay, red means we need to do it because the calculations say that we need to do it, because otherwise the power consumption is not sustainable, for example. But technologically we do not know how to do it. The yellow brick, the yellow color means we probably know how to do it. We are not there yet, but we have an idea of how to do it. Okay, and the white means it's done. We know how to do it. Okay, so the real problem was the thickness of the oxide. This equivalent physical oxide thickness for high performance diox had to go below 1 nanometer, but at the same time the power consumption, the static power consumption, had to remain under control, and this was the huge problem. The other interesting numbers are the ion. This is ion, nominal high performance NMOS saturation drive current. This was kept at 900 micron per micron, and this is ISD leak is what we have called IOF, the off current. So in order to keep these two values, we need an equivalent physical oxide thickness that goes down this way, and we do not know how to do it. And also in 2001 the roadmap goes down to 2016, so to today, and of course this is a long-term projection, so it's even less clear. The physical gate length was supposed to go down to 9 nanometers, and again the equivalent physical oxide thickness had to go at a half nanometer. So a half nanometer means 2 single atoms, a layer of 2 atoms basically. What happened, actually we already discussed it. The main thing that happened that was not yet there in the document of 2001 was this introduction of high K dielectric process. And you see the situation from a thickness of 1.2 nanometer of silicon oxide. This, you remember COX, the oxide thickness per unit length is is the dielectric permittivity over the oxide thickness. So the dielectric permittivity of silicon oxide is 3.9. They were able to use a different dielectric with a dielectric permittivity that was close to 15, which means that you can have for the same capacity a thicker oxide, and with a thicker oxide you can reduce the gate leakage, significantly. Okay, this is the main thing that happened and enabled to solve the problem of the oxide thickness. Regarding the other part that I mentioned before, that after 2002 approximately there was a decrease in the slight decrease in the frequency of operation, and in order to stop the increase of power consumption is shown here. This is a plot of the typical power consumption of high performance microprocessors from the 80s until 2008. Okay, I think you can see clearly the change in trend. Okay, at this point, up to this point, we have an increase of the power consumption that is typically due to the fact that there is an increase in the size, because the power per unit area more or less is constant. Sometimes you make some turbo boost of the operation of the processor, but the main factor from here to here was increase in the size of the silicon die, the total area of the chip. Then at some point you stop, and this means that here you go multi-core, F clock stops, and then you're able to, let's say, not go above 100 watt of power consumption per microprocessor. Of course, we are talking here of server class microprocessor. And this is an image of a CPU from 2009, 45 nanometer process, the class of Intel microprocessors that is called Nehalem. I want just to mention that basically a single chip is not really just a microprocessor. You have a lot of things that traditionally were out of the chip that now are integrated. In this case, for example, you have 4 cores, core 0 to core 3. Then you have a very large cache. Now, in today, almost half the total area of a chip is level 3 cache. Almost half the total area. So you have, in this case, very large cache. You have some input-output logic on the periphery that typically used to have on separate chips on the board. This DDR3 I/O controls the DRAM, and you have other I/O interfaces, and then of course you have some control logic. So let's say inside, chips are becoming much more similar to what boards used to be. Again, you cannot increase the clock frequency, but you have lots of transistors to play with. The other issue that is important is the power control of the different regions of the chip. This is something also relatively recent. It's happening in the last 10 years. In the chip that I've shown you before, the Nehalem 4-core processors, you typically have a control unit that provides different clock frequencies to the different cores, and also power gating. This is called power gating, this means that when a core is not used, it is switched off, basically. This is the best way to reduce power consumption. You basically switch off a core. If and this is very common in the case in which you have a multi-core processor. Sometimes when the load is not really high, you can really switch off some of the cores, and the great advantage in switching off the cores is that you suppress completely the static power consumption, which is a significant percentage of the whole power consumption. Okay. If you go slow, you only reduce the active power consumption, the dynamic power consumption. In order to completely suppress the static power consumption, you need to switch the core off. Then there is this frequency control, which is important because in the case of low load you can decrease the frequency. You can decrease the clock frequency. What's the advantage of decreasing the clock frequency? If you decrease the clock frequency, you can accept higher propagation delays, and therefore you can accept lower supply voltages. And in modern microprocessors, you typically have a control unit that, depending on the load on each single core, adjusts both the clock frequency and the supply voltage to the load, so that if you're able to reduce the supply voltage, you can significantly reduce the dynamic power consumption. Okay, so you have basically 3 different degrees. If you do not need one core, you switch it off. If you need a low load, you decrease the clock frequency, reduce the supply voltage so that the core can go slow and therefore have a low power dissipation. Okay, and in order to do that, you need to know at every time what is the temperature of the core, because the static power consumption depends a lot on the temperature, and therefore if you want to control the static power consumption, you need to adjust the supply voltage of the core as a function of the temperature at which the core is. Okay, so everything is becoming really complicated. Of course, at a higher level you do not see it, but at the level of the operating system, you need to at the level of the kernel, let's say not the operating system, one needs to take into account those aspects. Okay, I just want to mention this last point. Now, the 14 nanometer process is the process, the latest process from Intel, and what happens here is that, as we have observed at the beginning, we have very different types of requirements for servers and for mobile systems. For example, in this case, I mean, power consumption and leakage power is not actually an issue. You need to have high performance, and in mobile and in mobile systems as smartphones and so on, you typically need a very low leakage power because battery duration is a real issue. And for this reason, the other important aspect that aspects of novelty of the new technologies is that you have several different you have transistors with several different threshold voltages. For example, in the 14 nanometer process, you have 4 levels of VT N. So you can have transistors with higher VTN, higher threshold voltages, in order to reduce the leakage power, even if you reduce the performance, and you use them for smartphone class applications. And you can use transistors with lower VTN that have a high leakage power for server class applications, in which performance is the most important parameter. And so CMOS technology had to evolve in order to, let's say, embrace for a single technology different types of applications. Okay, and this is becoming more and more common. The next technology, which is the 10 nanometer technology, will have 6 levels of threshold voltages, so that it's really increasing. You can use the same technology for very low power smartphone processors and for servers, just by using the different transistors that you have in the same technology. Okay, now I can stop here for discussing this issue. Let me stop the video and then we can talk about the homework.